Hi and welcome. Today we're going to be looking at a projectile motion question where we have a football player who is kicking a football from a point 31 meters away from the goal and hopefully is going to kick the ball through the uprights and win the game for his team. So we are going to work some physics and see what happens. All right. Remember, anytime you're working a projectile motion problem, that the x and the y dimensions must be worked separately. That's the real key to projectile motion, is that the x and y dimensions are separate, are completely separate. And so they must be worked. They must be worked independently of each other, and you must use x um, x information to work with the x dimension and y information to work with the y dimension. There is one quantity which actually is the same in both dimensions, and hopefully you're thinking about it and remembering that time, of course, is the same in both dimensions because time is outside of our directional restraints. All right, so let's get started. First thing I'm going to do is just write down some. Well, I tell you what. Let's talk for just a second. So the ball is kicked. Here's the initial velocity. Here's theta, marking the angle, and the ball sails. And the way that we'll know whether it crosses above or below the crossbar and how far is to solve for delta y, that is the height of the ball, at this point right here. And that point is not just a point in space, but it's also a point in time. And so we need to find that point. We need to find how much time goes by in order for it to travel this distance. And once we find out the time that it takes it to travel that far, then we'll use that time value and discover and calculate the delta y, or the height. And then we'll subtract 3.05 for the crossbar to see how much higher it is above or below the crossbar, because it wants to know its height with respect to the crossbar. All right, so let's get to work. All right, so let's write down some givens. Our initial velocity is 21.0 meters per second. Our angle is 56 degrees. Our distance to the crossbar, and that's the only delta x that we're interested in. We don't really care. Yes, the ball sails beyond the crossbar, but we don't care what it's doing back here. We only care about if it goes over the crossbar or not. And so that means our delta x point, where we're interested in, is going to be 31 meters. 31.0 meters. Delta y is what we're looking for, and of course that means that we'll need to do a little bit of calculating at that point. So let's see. The acceleration due to gravity, which is the acceleration in the y dimension, is negative 9.81 meters per second squared. All right. So let's go ahead and let's find, first thing, let's take our VI and separate it into x and y components. So we're going to have an x component and we're going to have a y component to that velocity, and that's what we want to find out first. And so VI times sine theta, we're going to use our trig functions for this, will equal, you remember that sine is the opposite side, and so that's actually going to be VIY. So VI sine theta equals VIY, and putting in 21 for the initial velocity, putting in 56 for our angle, is going to give us the initial velocity in the y dimension, and go ahead and pause the video and do that calculation. Be sure you're in degree mode. And I got 17.4098 meters per second. Okay, so 17.4098 meters per second. So I'll just underline that to keep an eye on it. Let's see, let's go ahead and now do the same thing for cosine theta, and that will equal VIX. All right, putting in again 21 for VI and 56 for theta, I will find that VIX is equal to 11.7431. I'm keeping more decimals than I usually would because I'm doing this for a computer program, to check on a computer program, and it requires a certain number of decimals. So I will not be rounding until the very end, and we'll be keeping the several decimals on the way. All right, so we have that, and now that we know our velocity, remember that this is not just the initial velocity in the x dimension, but since there's no air resistance and there's no acceleration in the x dimension, that's actually the velocity the whole time. And if I know this distance, which is actually 31, if I know this distance along with how fast it's traveling in the x dimension, I can do some calculations and find out the time that it takes it to get to that point. So let's just do that real quick. I'm going to write down this equation, delta x equals VI times t plus 1/2 AT squared. Now, since the acceleration in the x dimension is 0, that's going to zero out this entire term. So all I'll be left with is delta x equals VI 11.7431 times t. And then this part is now 0, so plus 0, I'll just go ahead and leave that out. And then solving that, I get that time is equal to 2.6399 seconds. Again, keeping way more decimals than are actually reasonable, but that's what we have to do in this case. Computers don't care if you're reasonable, they just care if you have the answer within the some percentage of theirs. All right, so that means that the time to this point is 2.6399 seconds. So my time is 2.6399 seconds. It's not a 5, that's a seconds. All right, and so I need to know delta y at that point. Well, let's just use the same formula that we used a moment ago, except let's use delta y and use our y values. Right. So I'm going to say delta y equals VI, which is 17.4098, and I'm not going to write that, I'm just going to represent it there, times t, which is going to be 2.6399, plus 1/2 times negative 9.81 times t again, which is going to be 2 point and some change. But I'm rapidly running out of space, so I'm just going to write my 2 there, even though it's really 2.6399. So pause the video for just a moment and see if you're able to work out what delta y should be. All right, And according to my calculations, delta y should be 11.777 meters. Now, that is the total height, but the question says height with respect to the crossbar, which means we'd really like to know this little value right here. Okay, and so we're really looking for the value represented by the pink circle. So if we take that and subtract 3.05 meters, then we'll get a height with respect to the crossbar of 8727 meters. 8.727 meters, and that will be the height above the crossbar. So again, just for a quick review, we took our velocity, our initial velocity, and broke it down into the x and y components right there. Then we took the x component along with our x distance to solve for time. And then we utilized our time along with y velocity and y acceleration to get the height that the ball had at that point, and then subtracted 3.05 meters to discover the height above the crossbar, and that's ended up being 8.727. A follow-up question that is sometimes asked is the ball currently ascending or descending? And you would just solve for VF at that point. And if it's positive, then the ball is on its way up. If it's negative, then it's on its way down. So VF equals VI plus AT, substituting in a VI of 17.4098 minus 9.81 times 2.63, excuse me, 6399. There we go. And when I do that, I get a negative value of 8.487. Negative 8.487. And since it's a negative value, that means that the component of the ball's velocity at that point in the y dimension is downward, and so the ball is in fact on its downward trek, the downward half of the flight. All right, I hope that was helpful, and I hope that you have a great day. Thank you.